Today I'm going to show you some harder examples of solving trigonometric equations. So the first one here, we've got sine 3x plus root 3 cos 3x is equal to 0. So first of all, you'll notice that we've got a mix now of sine and cos. To enable us to solve it though, we need to try and get that down to just one trig ratio rather than the two. Now, what we do note, though, is that we've got 3x inside the both of them. So we really do need that to be the same to make it possible for us to use the technique that I'm showing you today. So first of all, what I'm going to do is just rearrange this. I'll leave the sine 3x on this side, and I'm going to take this over to the other side. So it'll become negative root 3 cos 3x. Now, notice if I now bring the cos over here by dividing it, because here, remember, it's being multiplied by the root 3. So I'm going to have sine 3x over cos 3x is equal to negative root 3. So now what you might remember from when you've done your work with the unit circle is that sine over cos is equal to tan. Now that's just only when the insides are the same, when the angle is the same, which we have here. So this now becomes tan 3x is equal to negative root 3. So you can see that we've gone from having two different trig ratios in the initial equation, and now we've just got the equation looking nice and simple with one trig ratio. Now I'm recognizing that my negative root 3 comes off the exact value triangles, and I can recall that it's from my pi on 6, pi on 3 triangle. So if we have that ready, so remember, there's always a 1 opposite the pi on 6. We've got a 2 on the hypotenuse, and so the root 3 is over here. And we've also got to think about the cast rule. So here I can see that tan is negative. So that's telling me that my solution must lie in the second quadrant or the fourth quadrant. So what I want to find is my related angle that I'll call alpha. Now, from the exact value triangle, I can see that tan pi on 3 gives me root 3 on 1, which is root 3. So that's telling me that alpha is pi on 3. So I'll just make a note of that there. So alpha is pi on 3. So now another thing that I have to take into consideration is that I've got a 3x here. So because x is between 0 and 2 pi, if we want to capture all of our solutions for x when we have a 3x in here, we need to go 3 times around the circle to get all of the solutions. I'll show you what I mean. So I'm going to start by saying that 3x can be equal to, so I've got my first solution here would be, so what we're wanting to do is get that angle, and then our second solution is this angle here. So this angle here is going to be pi minus pi on 3. And then the next one is 2 pi minus pi on 3. So now imagine that we've gone all the way around. We've gone pi, 2 pi, and then we're going to go around again. So 3 pi minus pi on 3. And then round to here would be 4 pi minus pi on 3. Then round one more time, we get 5 pi minus pi on 3. And our last solution, we've got 6 pi minus pi on 3. Okay, now we want to simplify all of those. So we're still looking at 3x. So think of bringing your pi over a common denominator. So that would be like 3 pi on 3, wouldn't it? So 3 pi minus 1 pi, 2 pi on 3. And here, think of this as 6 pi on 3 minus 1 pi on 3 will be 5 pi on 3. And then think of this as 9 pi on 3 minus 1 will be 8 pi on 3. Then we've got, this is 12 pi on 3 minus 1 will be 11 pi on 3. Then 15 pi on 3 minus 1 pi will be 14 pi on 3. Last of all, this will be the same as 18 pi on 3 minus 1 will be 17 pi on 3. Now, last of all, we don't want 3x, we just want x. So we're going to divide through by 3 to get x is equal to, now, if we're dividing each of these fractions by 3, effectively what we want to do is multiply the denominator by 3. So that's just going to become 2 pi on 9, 5 pi on 9, 8 pi on 9, 11 pi on 9, 14 pi on 9, and 17 pi on 9. So just to check that our solutions definitely are within the original domain that we were required to solve within, 17 pi on 9, well, if we had 2 pi, that would be equivalent to 18 pi on 9. So this is just a little bit less than 2 pi. So all of our solutions are within this range. So you can see now why we had to go around 3 times, because when we shrink them all down by dividing by 3, if we'd only looked at the first 2 solutions, we would have missed all of those 4. Okay, so that's one example of a strategy that you might use. So let's have a look at another question. So this time, I'm going to solve, we've got 2 cos squared theta is equal to 5 plus 5 sine theta. And once again, we're going to have theta being between 0 and 2 pi. Okay, so notice this time, once again, we've got a mix of sine and cos, but we can't use the same strategy that we did last time, because here we've got a cos squared and here we've got a sine, plus we also have a constant. So we still want to try and get it in terms of one trig ratio. And what we're using here is the Pythagorean identity. So that comes from the unit circle as well. Remember that we have the rule sine squared theta plus cos squared theta equals 1. Okay, so if I rearrange that to make cos squared theta the subject, I can say that it's equal to 1 minus sine squared theta. So this is our way of turning one, like cos into sine and vice versa. So here, I'm now going to substitute for this cos squared theta. So I'll have in brackets 1 minus sine squared theta is equal to 5 plus 5 sine theta. Now I just want to expand the brackets, and then I'm going to get everything over one side and equate to 0. So this is negative, so I'll bring everything over the right-hand side. So that's going to come over as 2 sine squared theta. Then I'm going to put my plus 5 sine theta. Now I've got 5 here, and this would come over as minus 2, so that simplifies to 3. Now notice we have a sine squared, we have a sine power 1 and then a constant. So you might recognize that we have a bit of a quadratic look about it here. So if we do a substitution, it'll make it easier to solve. So if I'll go let sine theta equal a. So now I'll just rewrite that as 2a squared plus 5a plus 3. So hopefully you're remembering how to factorize your quadratic. I'm going to do my little thinking table over here, put a, c, and b. So 2 times 3 is 6, and b is 5. So remember, we're looking at what multiplies to give 6 and adds to give 5. So I'm noticing that 2 times 3 equals 6, 2 plus 3 equals 5. So now I take those solutions over here. I have to do a little bit extra working, split that middle term up, 2a plus 3a, have my plus 3. And you might recall that we've got to factorize the first 2 terms together and then factorize the second 2 terms together. So now notice our brackets is common. So I've got an a plus 1 and a 2a plus 3. So using the null factor law, I can say that a plus 1 equals 0. So therefore a equals -1, or 2a plus 3 equals 0. So a would be -3 on 2. So remember though that a was really sine theta. So now come up here and I'm going to go, therefore sine theta equals -1, or sine theta equals -3 on 2. Now have a look at this solution here. Just recall that your graph of sine theta looks like this. The basic one is going up to 2 pi. And we have pi on 2 and 3 pi on 2 there. Goes up to 1, down to -1. So remember that sine starts at the middle, goes up to the top, back to the middle, down to the bottom, back to the middle. So your graph's going to look like that. So this is actually going to help us think through both of the, like any solutions here. So here I can see the first solution here, sine theta is equal to -1 when theta is 3 pi on 2. So I'll say that. But over here, in -3 on 2, that's -1.5, hey? So -1.5 is down here. Sine doesn't come down that far. It's only between 1 and -1. So this one gives us no solution. So for this equation, with that restricted domain, we had one solution. Theta is equal to 3 pi on 2. So there you go. What I want you to take away from that is the strategy of identifying when you need to use the Pythagorean identity to help get your equation in terms of one trig function only. And then secondly, being able to recognize when we have a quadratic setup, and you're going to use that technique there to make it easier to find your solutions. Well, I hope you found that helpful. Keep a lookout for more videos.